Hello, everyone. This is a TCS seminar at Jagiellonian University. Today, our speaker is Rob Morris from IMPA in Rio. So Rob is known for his contributions in random graphs, processes, specifically bootstrap percolation. He's an expert in probabilistic and extremal combinatorics. I think everybody in the community heard about the recent great result of his team improving an upper bound on the Ramsey number. So R of k is now less than c to the k for some c less than 4. And yeah, today I think we'll hear about some further developments in the Ramsey theory. Great to have you here, Rob. The floor is yours.
Thanks very much, Peter. Thanks for the invitation. Great to be here. Great to be there. So yeah, I'm going to tell you about some. So I gave a talk in the PCC last year, basically about a week after the result I'm going to talk about was proved, and so I wasn't really ready to talk about, but I sort of gave some ideas of some sort of hints of the method, and so today I want to sort of fill in the details and tell you actually how to prove this result. So I'll spend most of the talk sort of building up to it by talking about the previous stuff, and then we'll see how to in the second half of the talk how to finish it off. Yeah, please do ask questions if so. I wasn't completely sure exactly how many sort of young people or students or whatever, or people from other areas might be around. So I've included a little bit of background, but I guess it's mostly experts, so probably I'll go over that pretty fast. Yeah, so I should mention this is all joint work. So this comes from a long running joint project with Marcelo Campos, Simon Griffiths, and Julian Sazrabude, and then the final stuff I'm going to talk about is also joint with Paul Ballister, Bela Bolabash, Owen Hurley, and Marius Tiba. Okay, can I flick? Okay, so just to remind you what Ramsey's theorem says, here's a picture of Ramsey, I guess taken like 100 years ago. Right, that if n is sufficiently large, you R-color the edges of the complete graph, then you find a monochromatic clique of size k. And a few years later, this was rediscovered by Edish and Sekaresh, who gave this bound r to the k times r. Okay, so there's some pictures of Edish and Sekaresh. Maybe this one with Edish is a little bit before they proved this. I'm not sure exactly when the Sekaresh picture is. Anyway, looks like a teenager maybe. Okay, so Ramsey number is the smallest n, such that you can find this monochromatic copy of k. And let's start with two colors, just to get warmed up. So Edish and Sekaresh proved this bound of 4 to the k, which is just an easy induction. So I'll run through the proof in a second, just sort of to put things in the context I want to put things in for later. And the lower bound you color randomly. So I guess yeah, everyone here knows all of this stuff already. So I won't spend too much time on it. And the R color Ramsey number I'll denote with this sub R. Then so Edish Sekaresh proved this upper bound of r to the rk. And this lower bound I only discovered after we put the first version of the paper on the archive. Someone pointed out that this lower bound is not due to Lefman in the late 70s, but rather to Abbott in the early 70s. So yeah, I didn't know this until this sort of somewhat slightly obscure paper. So right, the upper bound is again this easy induction. The lower bound, when r is at most 3, you just color randomly. And then when r is bigger, then Abbott's observation was that you can do a product construction. So suppose you have 4 colors, you can take the coloring for 2 colors, blow it up to sets of size root n, and then put a little 2-color construction in each one, and that does better. So that gives this behavior. Okay, so the difference between the two bounds of a factor of log r in the exponent. Okay, so that was the setting for many years. Okay, so what is the Edish Sekaresh? How do you prove the upper bound? So just say that this picture we'll see again a bit later. So I want to think of it in a slightly different way than people think of it normally, or people describe it normally. So okay, we're gonna have this set X as the reservoir, and we're gonna try and build a red clique and a green clique and a blue clique. In each step, we're gonna take a vertex of the set X, and we're gonna place it in one of these cliques. and we're going to shrink X so that it's the common red neighborhood of A1, green neighborhood of A2, and blue neighborhood of A3. Okay, so each step we take a vertex from X and we place it in one of the cliques. Okay, and so we go down the size of X. If we choose the color to be the one with X has the most neighbors, we lose a factor of R in each step, and we have to do R times K steps to guarantee that one of these AIs has size K. Okay, so is it clear this this sort of slight restatement of the usual Edis-Ekeres proof? I hope it's all clear. It's all fine? Great. Okay. So so what's known? Over a series of 3 papers. So the first improvement was maybe due to Rödel in an unpublished paper, just by some sort of large constant factor or some log factor. But then there was important technique introduced by Andrew Thomason in the 80s, using quasi-randomness to gain some polynomial improvement over the upper bound. And then this was improved to a super polynomial factor by David Conlon in a famous paper in about 2009. And then that was more recently optimized by Ashwin Shah to give this this improvement the upper bound of e to the log k squared. Yeah, so this uses quasi-randomness, and in the later papers, sort of effective quasi-randomness. The details are pretty complicated. Okay, so what did we do a couple of years ago? We managed to get this exponential improvement that Peter mentioned in the introduction, using this quite different technique. So going back to the original Edis-Ekeres algorithm, instead of trying to find just a large monochromatic clique, we're going to find either a large monochromatic clique or a large red book. Okay, so for those who don't know what a book is, we'll see in a second. Okay, and this approach was optimized later by these 4 people: Gupta, Nyadye, Norin, and Wei. So they sort of rephrased this slightly inefficient algorithm we had as a more efficient induction, and optimized it and managed to get a very nice bound of 3.8 to the k. Okay, so that was all the introduction that I guess I would have normally done much more slowly. I mean, I hope for this audience then everything's all clear, and now we'll start with the more interesting part. Okay, are there any questions before I start the interesting part? Everything's fine. Great. Okay, so what is the proof for 2 colors? So if you just erase the set on the right from this picture, we get back to the original Edis-Ekeres proof. So the first innovation is to add this set Y, and so the filled in colors indicate that all of the edges are of that color. So all the edges between A and both X and Y are red, and inside A, and all the edges inside B and between B and X are blue. Okay, so this is the basic picture that we're going to maintain. And we're going to also try to track the density of red edges between the 2 sets X and Y. Okay, so I've denoted by this little p. So this is the density of red edges. And this pair AY on the right hand side is a red book. So a book is a red book, is a red clique, and a red complete bipartite graph going to some set. Okay, and the point of this is that if you have a red book where maybe the set A is size T, then instead of having to find a red clique of size K inside Y, you only need to find a red clique of size K minus T. Okay, so if you can sort of do this efficiently, then you can win. Okay, so hopefully that's clear. So what is the 2-color algorithm? So in each step, we're going to, what we'd like to do is take a vertex of the set X and place it in A. Okay, and then we would like the set Y will then shrink by a factor of P. P we're going to try and keep close to a half. So you should think of P as being at least a half minus little o1, say. Okay, and then we also have to shrink the set X on the left. Okay, and in the Edis-Ekeres algorithm, we really care how much we shrink X by. And the point about this algorithm is we don't really care so much how fast X shrinks. Okay, because we're not actually trying to make the set A have size k. We're only trying to make it have size epsilon times k, some small constant epsilon. And why is this a win? It's a win because the set Y is only shrinking by a factor of 2 every time we do this. Right? So our aim is to find a set A, a red clique A of size t, say, where t is some small constant times k, and Y is size 2 to the minus t times n. Right? So we managed to find a book, a t and 2 to the minus t times n size book. And if you can do that with t being constant times k, then an easy calculation shows you get an exponential improvement over 4 to the k. Okay, so this was observed certainly by Andrew Thomason in the 80s, and apparently it goes back even further than that. So maybe this was known even sort of to Erdős in the 60s or 70s, or maybe even earlier. Not clear. Okay, so this is the basic plan. We're going to try to do these constant times k steps, red steps, losing a factor of 2 on the right hand side each time. Okay, that's our basic plan. Now there are various things that can go wrong. So one thing could go wrong is the size of x could really shrink very quickly. I mean, what if inside x almost all the edges are blue? Right, so then we would shrink too fast, and we wouldn't be able to do this constant times k steps. Let's call it like delta k steps. But if that happens, then actually life is good for us. We can just take a blue step instead. Right, and we lose very little on the left because our blue is very dense, we're supposing. And if the set B gets the size k, then we're happy. Okay, so the first observation is we can assume that inside x, the red edges are actually reasonably dense, actually density bigger than a half. So let's just maybe think about that for a second. So I want to say if the blue edges inside x have density 1/3, say, then I'm happy to do a blue step. Why is that? Well, by doing k blue steps, I'll lose a factor of 3 to the k. But I'm only trying to do delta k red steps. So the red steps, even though they're quite expensive, they will turn out to be more expensive, there's very, very few of them. So you actually lose just an almost sub-exponential factor by doing them. Okay, so this is not entirely true. This is not actually how the proof works in the end, but just to get an idea, and the next proof will work this way. So well, okay, to some extent, right? So we don't really mind the blue steps if we lose a factor of 3 each time. Okay, so that's the first really nice observation. So inside x, our density is at least 2/3 red, say. Okay, so that seems like we're in really good shape. So we want to just do these red steps and we're happy. The bigger problem is that when we do a red step, we shrink both x and y, right? We have to change, x becomes the red neighborhood of the vertex we added to A, and y becomes the red neighborhood of the vertex we added to A. But then how do we control the density of red edges between x and y? Right, so that's the real problem. We go down to this subset of x and this subset of y. What happens if the red density between those sets just gets a bit smaller every time? And we're doing constant k steps, so if it goes down by 1 over k, it's already a bit of a problem. Okay, so we can only afford to lose. So our red density can go from p to p minus roughly 1 over k. Okay, at least 1 over log n. Okay, so what that tells us is this bad setting. So we have to worry about when that happens to every vertex. Okay, so every choice of x on the left-hand side has this strange property that if you look in its red neighborhood on the left and the right, there are fewer red edges there than you expected. Okay, so you can think of this as being, so you can map this into sort of d-dimensional space, and think of this as being the inner products of these sort of red neighborhoods are kind of negatively correlated. They're pushed away from each other. Yeah, so at the very end of the talk, I'll state a conjecture about such sort of negatively correlated points in d-dimensional space, which we have not been able to prove, but I think is sort of perhaps one of the most interesting things to come out of this project. This was our sort of our main attempt to solve this problem for several years. Um, so what would you hope for in that situation? So what good thing could happen if your points, your sort of your red neighborhoods on the right hand side are kind of pushed away from each other? Well, imagine a bunch of points in d-dimensional space that maybe on a sphere, say, just to make it easier to think about, where their inner products are sort of typically negative. Like 2/3 of their inner products need to be negative. That 2/3 is the same as the red density inside X, by the way. Okay, so what you know is that the red edges inside X have red neighborhoods in Y that are negatively correlated. Okay, so you have these 2/3 of these pairs of points have like significantly negative inner products. Well, one way you could do that is by clustering the points. You could take, sorry, let me close that. Yeah. Uh, you could cluster the points together in little groups. So maybe anything on a circle, you could take 3 groups of points all very close together. If you take 2 random points, then they, with property 2/3, they'll have negative inner product, like significantly negative inner product, right? Think of 3 points on a like an equilateral triangle in a circle. Okay, so what we could do is to cluster the points. Is there any other way that you could cluster the point that you could make this happen? The conjecture says no. The conjecture says that basically in order to have this property, you have to cluster the points in some way. Okay, it doesn't have to be such extreme clustering as an example I said. We have examples where actually the points look sort of somewhat pseudo-random. For example, you can take the famous Kahn-Kalai counterexample to Borgstadt's conjecture, which is a sort of pseudo-random-ish set of points in d-dimensional space, for those who know it. And that has this property. There's property that most pairs are have sort of a significant negative inner product. And there isn't really such obvious clustering. However, there is some clustering. So what you have is in certain directions. So if your points were randomly placed on the sphere, in every direction you'd see a Gaussian. If you like project in one dimension, you'd see a Gaussian, right? If you picked randomly. So there are certain directions in this Kahn-Kalai construction where instead of seeing a Gaussian tail, you see an exponential tail. So basically, it's because when you do this construction, it involves some quadratic function, and the quadratic turns the e to the minus x squared in the Gaussian to a sort of e to the minus x. Okay, so it's not obvious that happens. I mean, one can write it down in a few lines. It's not too difficult to check. So a strong version of this conjecture would be that's really the worst thing. The most efficient way to create these negative inner products, 2/3 your products inner products are negative, is to take this Kahn-Kalai construction and then you get these exponential tails. So the exponential tails in certain directions, how can we use those? How is that? Why is that a good thing? Well, I guess maybe go back to if a bunch of points are clustered together, what's that saying? That's saying their red neighborhoods are very positively correlated. And that corresponds to a subset of X and a subset of Y that have much higher red density than P. With this exponential tail you get in certain directions of the Kahn-Kalai construction, it's not as big of a density boost, but it's still there. So you can turn these special directions into subsets of X and subsets of Y, pretty big ones, that have a higher red density across, and then the move is just to go into those subsets. Okay, so if the red edges between x and y are not random-like, if they exhibit this kind of clustering, then there should be this density boost available. You should be able to go into a subset of x and a subset of y with much higher red density. And why is that good? Well, it's good because in every future step, instead of getting density p, instead of losing a factor of p on the right, you only lose a factor of p plus whatever you gained. Right? If you have higher red density, then your set y is shrinking slower.
So I have a question.
Yes,
When you
please.
put it into this d-dimensional space, you put just neighborhoods of x, or
Just yeah.
just
Yeah, sorry, thank you. That's a good question. So yeah, so an easy way to do this is into n-dimensional space is or size of y-dimensional space. Yeah, just to map each point to -1, 1 to the y. So the indicator function of, or characteristic function, whatever, of the neighborhood. So red edges to y get 1, blue edges get -1. Yeah, thanks. And that maps things into, yeah, so both is important, but that maps things into sort of n-dimensional space. And it's got this very strong, because these inner products are like -1 over k. So it's way 1 over log n, right? If it were random, you'd get inner products of ±1 over root n. And they're ±1 over log n. So really, I think the right way to think about this is to project randomly into log n squared dimensions. Right, so by, what's it called? Lindenstrauss, what's it called? I forgot. This like random projection thing. Or it's like weak regularity. It's basically the same thing. So you can think of this as living in sort of d-dimensional space where d is log n squared, which unfortunately is too high to use any sort of nice properties of low dimensions, really. But what it means is then you have some points in d-dimensional space where 2/3 of the inner products are like -1 over root d. They're sort of right at the correct sort of like one standard deviation negative. But yeah, so the simplest way is just to take these +/-1s. There are other ways to do it using the eigenvectors of the bipartite graph. So there are more sort of more complicated ways. But basically, just think about -1, 1 to the y. Yeah. Thank you. Yeah, that's an important point. Okay. So that's sort of what you should be thinking about this proof as working. Our proof in reality didn't work exactly like that. So we were unable to prove this density boost. So instead, what we did was we got some much weaker density boost, which is almost trivial to get. And so the density boost we get is just, look, you either go into the red neighborhood of this x and y or the blue neighborhood. And then on the left-hand side, you go into the red neighborhood or the blue neighborhood. So it's sort of very simple. And by some sort of miracle, it happens to beat Eddie Securesh. But it's sort of more by luck than judgment. So this worked and fantastic, but it's not really the right proof. So I sort of want you to just forget about how the proof actually worked for two colors, and just think about how we wanted the proof to work, because for our colors, it's going to work the correct way. So I'm going to tell you the correct proof. The correct proof for two colors is the one I'm going to tell you in the sort of second half of the talk. Okay, so right. So this is the idea. The idea is that we would like to do a red step and keep the density across being p. There's two ways it can go wrong. Either your density of red edges in x is smaller than 2/3, in which case, fine, do a blue step. Or your red density x is bigger than 2/3, in which case, if you can't find a good red step that keeps the density p the same, then you must have some large density boost. Right? I think that should be true, and okay, we're going to prove some version of that in the second half. Okay. Are there any questions about this proof? Yeah, on my next slide, I'm going to actually tell you the algorithm. So maybe we can just see that again. Oops. So, okay, so what do? So we start with A and B empty. We repeat the following steps. If the blue density inside X is large, then we can do one or in fact many blue steps in one go. Otherwise, choose a vertex X. If you can do a red step without losing too much from the density, this alpha, then we add it. Yeah, there's some subtlety in the alpha. The alpha needs to be chosen carefully depending on the current density P. But let's not worry about that too much right now. If you can do that and do a red step, and if not, then you can do a density boost. And the density boost we use is actually extremely simple. It's just replace, so add X to B, replace the left-hand X by the blue neighborhood, and replace Y by the red neighborhood. Okay, so super simple. Okay, and then you just use some analysis and it works. Okay, so that's the setup for the two-color proof. Okay, so yeah, that's supposed to be. This is all supposed to be sort of motivation for to help you understand the later proof. Yeah. So if there are any questions, then please do ask. The basic idea clear, I hope. Right, that we're trying to do these. We're trying to do these this move, and there are two things go wrong, and hopefully we have a solution for both. Okay, so this doesn't work at all for R colors. So if we could prove this sort of optimal conjecture about the density boost, about these points in d-dimensional space that are negatively correlated and have a density boost, if we could prove that, then we can maybe do 3 colors, maybe even 4 colors, but it breaks down very quickly. This gets very inefficient for more colors. So, okay, so let's talk about R colors. Okay. So what's known? So I told you already that these bounds by Edison-Sekaresh and by Abbott. And there were recently some improvements on the lower bound. So there's a breakthrough result by Connon and Ferber, and then some follow-up papers by Yuval Vigdasson and by Sorin that improved the constant in the lower bound. So they instead of just doing this simple product construction, there's some clever new constructions. In the case R equals 3, so mixing some algebra with some randomness, and then using this product construction of Abbott, then you can blow these up to give an improvement for all R. But for the upper bound, there's really been no improvement at all. So even the method of Thomason, the quasi-randomness method, doesn't appear to give anything for this problem. I talked to David Connon about this, and he said that he's pretty sure that his method could be extended to R colors, but the details are much more complicated, and he never actually managed to get around to writing it down. So yeah, it's possible that you can get some polynomial improvement or some super polynomial improvement using the method, but I mean it's very unclear to me how you would extend his method. I think he really needed some extra like clever ideas to do it. So yeah, it really seems like it's a harder problem. And our method for 2 colors also sort of breaks down pretty quickly. Okay, so nevertheless we managed to do it. So this is the main result that I want to tell you about today. Okay, so we're going to get some exponential improvement for every fixed R and sufficiently large K. Okay, and this constant delta we get depends on R, not in a terrible way, but it goes to 0 as R tends to infinity. So I'll tell you, I'll state at the very end a more precise version, telling you what delta and sufficiently large means. Okay. Okay, so this is our aim. And yeah, this is by Balog, Bolobash, Campos, Griffiths, Hurley, Morris, Sasrabude, and Tibo. Okay. Yeah. Yeah, so this sort of monstrosity of a co-authorship arose because so three things in the proof. So first, Marcelo and Julie and I came up with the correct conjecture, which I'll tell you about in a minute, geometric conjecture. And then Owen was visiting Rio, and he and Simon came up with a very sort of promising approach to try and attack it. And then in September last year, Paul and Bela and Marcelo and Maris and I were in Rome for a couple of weeks and managed to sort of push through the approach that Owen and Simon had started. So this was happening in three different steps. Okay. Right. So what is the plan? The plan is, so instead of picking a color red and finding a large red book, I should perhaps say that, yeah, so how do we choose the color to find the book in the two color case? We just chose the color with more edges. Okay, so we pick the denser one, basically. Okay, so yeah, that was the asymmetry that we added. Here we're gonna have a symmetric version. So one sort of weird thing about that proof is that we're only looking for a red book, not a red book and a blue book. And the reason for that, if we come back to here, so why are we only looking for a red book, not looking for a red book and a blue book? Basically, because it focuses the attention. We just try and do one thing. Like if we're trying to control the red book and the blue book, then we don't know, okay, maybe we start doing the red, but we also want the blue to be okay. It becomes very complicated. It's very hard to keep track of what you're doing. It's not at all obvious how to even get started. If you focus on the red book, then it's like, okay, I'm just trying to do red. Like this asymmetry really seems to simplify the picture, right? The blue steps are sort of trivial. That forces this large red density that gives us this geometric picture. Then it really seems to help to focus on one of the colors. Right, but here, right, to do our colors, we can't afford to just pick one of the colors. We really have to sort of think about all of them. Okay, so it's going to make life in some ways worse for us. And so the key thing is going to be to come up with this sort of correct geometric lemma that gives us this density boost we wanted. Okay, so it turns out that we have a different geometric conjecture and now actually lemma that gives us this strong density boost we wanted in the two color case and we're unable to prove. Instead of getting this very weak, simple density boost, we have a much cleverer one. Okay, and this is like the main thing that I want to try to explain to you. And also gives a much shorter proof. So in some sense it's a less elementary proof. Like there's some sort of the main this lemma is more technical than the other proof was sort of super elementary. This one is perhaps in some ways yeah. Well, okay, you'll see when you see the statement. You can judge for yourselves whether it's more or less complicated, but it's certainly much shorter. Because once you have the correct density boost, then the rest of the argument just flies through with no problems at all. Then it becomes really very simple. Okay. Okay, so this is our aim. So here is the picture. So you'll see it's basically the same as we saw last time, except instead of having one book, we're going to have our different books, one in each color. Okay, so we're going to have the same reservoir set X. We're going to have these, perhaps I should have called them, sorry, this B should be AR, I guess. So we're looking for R different cliques, one in each color. And we're looking for R different books, one in each color. Okay. So what is our aim going to be in this picture? Well, I guess we would like to, in each step, do either a red step or a blue step or a green step or whatever. What does that mean? So what is a red step? Red step means we pick this vertex little x in big X and we move it into A. And when we do that, we have to shrink X into the red neighborhood or some subset of the red neighborhood actually. And we have to shrink Y1 into the red neighborhood of little x. Again, or some subset. Okay, and then the rest of the sets can say the same. The other yi's can say the same. Okay. Okay, so in each step, that's what we're going to do. It's very simple, like Eddy Sekaresh. Pick a vertex in X, put it in one of the cliques. Okay, shrink the sets as we have to. Okay, so how are we going to choose this vertex X? Well, right, we don't want the set X to shrink too much. That's one thing, right? It can shrink by a decent amount, not by a factor of R or something. It can shrink by a much bigger factor, but it shouldn't disappear, right? So our algorithm ends when the set X vanishes. So we want it to sort of not shrink too quickly. More importantly, we want to maintain these densities of edges between X and the yi's. So let's imagine at the start that the density between X and yi is 1 over r for every I. Right? It's not actually obvious that we can do that. Right? So there's some issue there. Right? We don't know at the beginning that our coloring has density 1 over r in every color. Right? We're just given some coloring. But okay, we have some densities, P1 up to PR of edges between X and yi. It's okay? And we'd like to maintain those. We don't want them to shrink. So when we do this red step, when we go into this neighborhood in X and neighborhood in Y1, right? We want there to be lots of red edges between them. Okay. So how can we think about this? Well, what we're interested in is, say, let's just think about X and Y1. So we can again map the red neighborhood of each vertex of X. So for each vertex in X has a red neighborhood in Y1. We can map those neighborhoods into n-dimensional space just by taking maybe 1 minus 1, or actually probably it's 1 minus 1 over R and minus 1 over R, or whatever it takes to make it nice and balanced. Okay. Okay, so we map those into n-dimensional space. And what we're interested in is the inner products of those vectors. If the inner product of those vectors is negative, that means that placing one of those points in A and keeping the other one in X is going to lead to a lower red density. So what we'd like is to find a point to put in A and many red neighbors of that vertex in X, such that those inner products are positive or at least not too negative. Right? Okay, that's what we want. So how are we going to do that? The problem is we don't have any control over the edges inside X, inside capital X, the colors of those edges. So even if we find a vertex which has, please.
Question, sorry. So
Yeah.
even if you find these vertices that they have a similar neighborhood, like a positive
Yeah.
correlation, don't you need somehow that they have red edges, like that the chosen X has red edges to the other that you found, like because you want to put it in.
Yes. Yeah. Exactly. So this is a big problem. Yeah. So if we sort of ignore edges, the colors inside X, then we just want positive correlation. But actually, it's worse than that. Yeah. We also want red edges inside between those vertices inside X. And what that means is, and we don't have any control over those edges at all, right? X is just some terrible coloring that's given to us. It's got no correlation with the edges across. Life is horrible. So here's the idea. Suppose we can find many pairs x, y inside X, such that their inner product to yi is positive for every I. What if they're positive correlated in red, in blue, in green, in every color? Then whatever color the enemy puts between that pair, that's good for one of the colors. Right? So what we want is, we would like a positive density of pairs in X such that all our pairs of vectors have positive inner product, or at least not too negative. It could be a little bit negative. Right? Okay. What could we hope for? Well, okay, each one is like half the pairs are positive inner product. So maybe we can get 2 to the minus r or something. So for a fixed r, maybe a positive proportion of pairs in X have this positive inner product in every yi. Right? It doesn't seem so unreasonable. Okay? If we can find that, if we can find a positive density of pairs like this, good in every yi, then what do? We just take the color that appears most often in those pairs, pick a vertex of maximum degree in that color, in that graph, and do a step of that color. Right? So the geometric conjecture says if you can't do that, then you should be able to get a density boost in one of the colors. Right? If they're not sort of nice and random and happy, if they're sort of negatively correlated in this horrible way, then that should imply some kind of density boost. Okay, so I'm now going to try to say that in symbols instead of in words looking at a picture. Okay. So I just need one piece of notation. So I've been talking about density of edges between these two sets the whole time, which is what we do in the first paper. Here we can do something better. Here we can look at the minimum degree. So instead of controlling the density of edges between red edges between x and y1, right? But instead of controlling this sort of average degree, I want to control the minimum degree. Okay, and this pi is just telling you the minimum relative degree in color I to set yi. Right, so ni of x is a neighborhood in color I, and yi is set I. Okay, so if this is a half, then every vertex has half its edges to yi being color I. Okay, that's the thing we're going to control. Okay, here is our aim. So we want to find a vertex on the left-hand side and a subset of the left-hand side such that the minimum degree in this subset to the color I neighborhood in yi doesn't go down too much. Right? So what we're really going to do, we're really going to sort of find a positive density of pairs which have almost positive correlation in every yi. Okay, this is this first case. Okay, so we're gonna find some subset of the pairs that are good in every color. Okay, and if that set is big, if we actually have a constant density of pairs like that, then we just pick the color with most edges and do a step in that color. Okay. Okay, so this is just what I said before on the previous slide. If you can find this positive density of pairs good in every color, just pick the color that appears on those edges most often and do a step in that color. You use a constant fraction. Oh yeah, so let's just see why is that good? Suppose we can do this every time, right? So suppose in every single step of the algorithm, we manage to do this first step. Why are we happy? So how big will these cliques be? Well, we're losing a factor epsilon, just some constant in x in every step. So we can do like epsilon log n steps. Right? So one of the r cliques has size epsilon over r log n. So still constant log n. Right? And the yi's are only going down at the correct speed. Right? So one of the biggest clique will have will form a big book.
Isn't it just one yi going down every step?
Yes, right. So you only the yi only goes down when you place a vertex in the corresponding clique. Yeah. So if there are t vertices in A, then yi should have size 1 over r to the t times n. Now, you might notice that I cheated there. It contradicted something I said before. Yeah, so there's what I said before was we couldn't guarantee necessarily, we're given this coloring, we can't guarantee that every color has the same number of edges. Maybe there's a lot more green edges than red edges. So maybe the initial density of red edges is smaller, but maybe the red clique is the one that we're given at the end. So that's bad for us, right? What if the red clique is very big, but the y1 is actually much smaller because the density of red was much smaller before? So this is sort of a real issue. The way to solve it is just to start the proof by applying Erdős-Székely steps until you get to a coloring that's regular, sort of has many edges in every color. If any color does not appear very often, that implies a boost in some other color, like some other color has slightly larger density, and then just like do an Erdős-Székely step in that color. So you have to first pre-process the coloring by running Erdős-Székely until you end up with something that's very regular. And then once you have a regular coloring, you can do this. Now this is what this means, for example, is suppose you want to use this algorithm to just find a large book and not a clique, it doesn't work because the coloring might not be regular. So this problem of not controlling the density of the colors in the original coloring is a real problem in some cases. Here we're saved by the fact we can do Erdős-Székely. Okay, so you start off with doing Erdős-Székely. Once you're regular, then you do this, and then what I said makes sense, right? Then if we're losing a factor epsilon every step, we can do epsilon log n steps. Whichever clique is then big, the corresponding yi is also big, right? Because we were controlling at every step the density in between x and yi for every I. All the densities stay very close to 1 over r. Is it okay? Okay, so now we come to the real issue, the real business, which is what happens if this fails. Okay, I guess I still have 10. I'm allowed to go to quarter past, is that right?
Yeah, it's more than all right. Actually, the talk is usually between 60 and 90 minutes. So
Oh, right. Okay. So I'll go slowly. We'll see how long it takes. Yeah. Sorry. Yeah. I planned for 60, but that's fine. Okay. So, okay. Now we come to the real meat. Okay. So suppose x prime is small. So as we can't find this like positive density of good pairs, then we want to find this density boost. So we claim there exists a color such that this min degree density goes up not by just alpha, a small amount, but by lambda times alpha. Can you see when I highlight here? Yeah, great. Yeah, so the amount we're willing to lose is some alpha. Okay, actually, this alpha, right? Maybe it depends on the color, but I'm doing some slight simplification here. But anyway, let's just okay. So you're allowed to lose alpha in one step. Alpha you should think of as being 1 over k. Okay, you're going to do constant k steps each time. So if it's like 1 over k, then you're happy. Maybe a little bit smaller, little o 1 over k. Okay, so we're going to gain instead of losing alpha, we're going to gain lambda times alpha, where lambda is at least some large constant, right? Depending on r. So like whatever 10 to the 10 times r to the 10 or something, whatever. Okay, so this is our density boost. Then some color, our density is going up by huge constant times are sort of what we're allowed to lose. Okay, so for each density boost, it's going to take the enemy sort of huge constant number of steps to get back to where he started. Does it make sense? So yeah, so if we go up by this lambda times alpha, it's going to take the enemy lambda steps to get back to the same density again. So the enemy's going to have to do, if he gives us this density boost, he's going to have to do sort of lambda steps that we like. Otherwise, our density has been boosted forever. Okay. Does it make sense?
so this vertex x is so this vertex x and x prime is fixed before, and then there are these two cases.
Yeah, no, sorry. So yeah, so perhaps I'm trying to simplify a bit too much. So yeah, so we're either going to find an x and x.
Yeah.
Oh, yeah.
Okay.
So what we're gonna find in this case is we're
Okay.
gonna find a vertex x and a set x that do have this property, and moreover, that there's a special color that we get boosted in.
Okay. Okay.
So we're gonna not lose too much in any other color, and in this color we're gonna gain some huge amount. Yeah, yeah, we really want both. Yeah, because when we do this, then we are going to lose this little bit, right? Because yeah, right. Okay, so how much can we afford to lose in the size of x when we do one of these steps? Well, this is equivalent to doing lambda normal steps, right? So the enemy has to give us sort of lambda normal steps. So the enemy's only going to be able to do this 1 over lambda times. So it's okay if we lose a factor of epsilon to the lambda, right? If the enemy does epsilon step epsilon step epsilon lambda times, and then one of these, okay, it's just the same thing twice. So what we want to beat is epsilon to the lambda, and what we get is something actually quite a lot better, something that's really sub-exponential. Actually, this is important. If we just got exponential here, this would not quite be enough. We need to get something here that is sub-exponential for some slightly technical reason. But this epsilon to the lambda, you can see that exponential is roughly the right the right level, right? The right right. That's so notice that. Or perhaps it's not obvious. If the points really were random, if the neighbors really were random, then in this sort of d-dimensional world, then we'd expect to get a Gaussian here. This would be e to the minus lambda squared. So getting to exponential is non-trivial in the first place. And we saw in the other conjecture, this Kahnke-like construction shows you can't do better than exponential there. But here you can. Here you can get down to really this sub-exponential, and that's what we need to make it work. So this e to the minus root lambda is essentially irrelevant. Like it doesn't hurt us at all. Yeah, so this is all that we lose essentially nothing when lambda's large. Okay. Right, so this is a huge density boost and an sub-exponential, therefore basically trivial loss in the size of x. So if we can do this, sorry,
That's a function of R or K only?
yeah, sorry, everything's a function of r.
Everything is a function of R.
Nothing's a function of k, unless
Okay.
stated. Everything is a function of r. Yeah, yeah, all the constants depend on r. Thanks. Yeah, yeah. So yeah, this big O is it's some polynomial in r, I think. And then I'm also cheating slightly because there's an exponential in r in front of it, but whatever. Okay. Okay, so if we can do this, then life should be good, right? Then we can just run this process. The enemy cannot do too many of these density boosts. So, okay, so there's another subtlety there, which also appears in the 2-color paper. This alpha should depend on the current density. So we basically we increase the alpha. It's proportional to the current value of pi. What this means is the enemy can only really do sort of log k of these bad steps more than more than are paid for. So by sort of choosing this alpha not to be constant over the whole proof, but depending on where we are, what this means is that the enemy just cannot do too many density boost steps. They're sort of forced to do a trivial number, a sort of unimportant number of density boost steps. What this means is almost all of the steps are of this nice form that we like, and we already argued in that case that we're happy. Right? So if we can prove this, then we're basically happy by some fairly simple argument. Okay? No need for very complicated calculations like in the first paper. you just do sort of the obvious thing and everything works fine. Okay, so this is really the crucial thing, that we can find this special color with this big density boost. Okay, so how do we do that? So now we come to like the key lemma of the whole thing. Oops. Ah, yeah, sorry, that is we get density boost in color L. Sorry. Right. Okay, what is the key geometric lemma? Okay, so let's state it in this sort of in this general context. So this is all we really use. So imagine you've got two independent random variables in some finite set X. So X will be our set X. Okay, so it's the set on the left. We're picking, and U prime will be uniform, independent random variables. So just think of these as being two random vertices of the set X. Okay, and we can have R different, excuse me, functions from X to R to the N. These are functions are just the neighborhoods in Y1 up to YR. Right, so each vertex in X has a red neighborhood A1, a blue neighborhood A2, a green neighborhood A3, and so on. So Y1, Y2, Y3, which, as we said before, we can map into our in n-dimensional space in just this trivial way. Right, give plus to colors of edges of the correct color, minus to edges of different colors. Okay, so this picture that we had before, let me just go back to it. This thing just maps directly into this setting. We're going to pick two uniformly random elements of X, and each vertex little x, corresponds to, there's R functions that correspond to their neighborhoods in Yi of color I. Right? Okay. Okay, so that's we just put the setting, the picture we had in some geometric setting. And what do we want? We want something like this. So what does this say? This says that, so this probability is just the proportion of pairs, right? It's the density of good pairs, which we said we want to be positive, right? So when is a pair good? It's good when, oh, sorry. If I can, there we go. Right? The inner products of these two vertices are positive, or at least not too negative, in every color. So this second half, this intersection over I of these inner products being positive, that's just saying, so if you forget the first bit, that's just what we wanted. We wanted that to be this probability to be at least a constant, to be at least epsilon. Right? That's telling us what is the density of good pairs inside this set X. Right? So there's this lambda in this statement. There's at least -1. Suppose lambda equals -1. Well, then this first bit just follows from the second bit. And if lambda's -1, then we just get some constant on the right. So when lambda's -1, this is just exactly the first case, the good case. Right? So this good case here. The density of good pairs in X is positive, so we can just pick a vertex and a color. Okay. Okay, that's the case when lambda is -1, when lambda is small. So when does this break down? When this thing stops being constant. So when lambda is very large. When lambda is very large, then this is saying that actually in color L, you get a large probability, a decent probability, e to the minus big O root lambda, of having large inner product in color L and still getting not terrible inner product with everyone else. Okay, so this is just putting in some sort of probabilistic or geometric language the thing that we wanted. We want either a positive density of good pairs, good in every color, or we want a non-terrible density of pairs that are good in every color and really good in one of the colors. Right? In this latter case, we can do this density boost step. Okay, so this is the lemma that we want, just in some sort of slightly more abstract setting. Okay, right. So roughly speaking, right. So why am I saying negatively correlated? Well, what are we avoiding? We're avoiding in this R-dimensional space the positive quadrant, right? We're saying that these functions you can sort of look at for pairs of points, their inner product in the R different dimensions, R different worlds, and if they were independent of each other, then you get density 2 to the minus R. Each one is sort of positive inner product with density a half by the way we chose them, or for some other reason. So if they were independent, then you get 2 to the minus R. This is saying you really don't get something much worse than that. Right? That really these things are pushing away from, there's essentially like a density little o1 of these pairs that are sort of okay in all colors. That if they're good in one color, it forces them to be bad in another color. Right? They're negatively correlated. And it's saying that if that happens, then at least one of the functions has to be very far from random. It must exhibit this clustering, this sort of large inner product with much better than Gaussian density. Okay, so this is like the general picture that you should feel. But what's Ramsey theory really about? It's saying that negatively correlated functions can't be random-like. Okay. Okay, so how do we prove this lemma? Okay, so here's the first observation. So it looks a bit technical, but it's actually not so bad. So this is just like the moments of these R functions, right? So the TI can be anything, right? Saying all of these moments are positive. And this is actually surprisingly easy to prove. You just basically write it out as tensors and do a tiny bit of algebra, and it falls out within like a few lines. So it looks like a slightly scary thing. Actually, it's just a few lines of algebra. Okay, so there's nothing really crazy happening here. Okay, so yeah, so this is just a property of sort of yeah, geometric space of the inner product basically.
Just inner product and uniform random.
Yeah, right. Yeah.
Mm.
Yeah, there's really like nothing happening here at all. This is just sort of just a fact about the world. Okay. And yeah, and very easy to prove. Like really just a few lines. Yeah. Okay, so these positive moments. So now here comes the really crucial idea. The sort of that I would like to give credit to Paul Ballister for. We consider this function. Now, what is special about this function? This sort of weird product of Cauchy's, right, over different colors. The point about it is its Taylor expansion has non-negative coefficients. Okay, this is not completely obvious to see at first, but it just follows them immediately from, if you define cosh root x in the obvious way using the Taylor expansion, you just see it immediately. Okay, so just a fact about the function cosh. Okay, and what does that tell us? That tells us that the expectation of f of the inner products is positive. Why? Because you just write it out as a Taylor expansion and then use linearity of expectation and the fact that all of the moments are positive and all the coefficients are positive means you're positive. Okay, so this is just a consequence of this observation. Because all the moments are positive, then if you write out this function as a sort of as a Taylor series, then because all the coefficients are non-negative, and the expectation of each monomial is non-negative, just the whole function is non-negative, right? So you get the expectation is non-negative. Okay. So that's fine. But then what we need another nice property of this function, and it's this.
So what did you mean by set the sigma I at the previous slide?
Oh, sorry, this is fi. Sorry. Yeah, sorry, I copied and pasted this one this morning and forgot to change it. Sorry, the sigma I is the fi's. Sorry. That's, yeah, so in the paper they're called sigma i's. I apologize. Ah, and I call it f as well. Sorry, I'm doubling my f's. Terrible. Yeah, I'm sorry. This is the first time I've talked about this with slides, and so I made these late last night. Yeah, and early this morning. I apologize. Yeah, sorry. Yeah, sorry. So Zi is fi u inner product fi u prime. And sorry, and this f is, yeah, not the same as those f's. Sorry, I should have renamed it. I apologize. Yeah. Yeah, sorry, I was going to and then forgot. Yeah, so I also got distracted last night by Brazil losing horribly at football to Argentina. Um,
No, like the F I got it. The sigma, it's okay. I mean,
yeah, sorry. Yeah, the sigma I is fi. I apologize. Okay, so we have this expectation of these inner products is positive over u and u prime over this this uniform choice, and then we also have this property. Now, what's this saying? This is saying that f, in some ways, approximates this positive quadrant, this bit of the world. So if any of the xi's are negative, like reasonably negative, then this function is small. It's at most -1. Right? So this function is negative everywhere except in this approximation of this positive quadrant. And that's the thing we care about, right? We care about this positive quadrant, right? These guys that are at least -1 everywhere. And it doesn't grow too fast. So it only grows like e to the root x, basically. Or e to the sum of the root xi. Yeah, all the r's are constant, so you can sort of think of them as being, just 1 or something. Okay, so this function, it's minus everywhere outside this positive quadrant, and it doesn't grow too fast in the positive quadrant. I now claim that's just enough just to prove the lemma, the key geometric lemma. Why? Well, remember the expectation is positive. And what we're trying to prove is there's like an epsilon of weight on the positive quadrant. Suppose there isn't an epsilon of weight in the positive quadrant. Suppose there's 0 weight. Well, this lemma tells us that the function is negative. So the expectation can't be positive. Right? You have to put some weight on the positive quadrant to make the expectation positive. Because this function is negative everywhere outside the positive quadrant. Right? Positive quadrant up to some little error that we're okay with. Moreover, okay, what could go wrong? Maybe you have some tiny weight on the positive quadrant, but the f is huge there. But this tells us not true. F is not too big unless the weight is really far out. Right? Unless one of these xi's is really big. And one of these xi's being really big is exactly what we want. Okay. So actually, just this magic function plus a tiny bit of algebra gives us this key geometric lemma. Right? So it's just this, these properties are not hard to prove about this function. This is just sort of an easy calculation gives this
why
these
isn't
bounds.
it the problem that you have this slow positive growth already slightly below the 0?
Ah, yeah,
Isn't it?
sorry. So this -1, so we just multiply the thing by 3r, so the -1 becomes the -3r.
Uh-huh.
Yeah, sorry. So yeah, I perhaps cheated slightly. The zi's, if we just multiply zi by 3r, then the same thing's true. You just lose, yeah, you just lose a factor in your sort of big O here, maybe in front. Yeah. So the 3R you can just rescale, so it's yeah, so it's okay. Yeah, so this definitely costs you in the final value of delta or k or whatever, but just by a polynomial. Are there more questions? So I hope it's reasonably clear, right? So you have this function in r-dimensional space. It's sort of negative everywhere outside the positive quadrant, and its expectation is positive. So you must have some weight in the positive quadrant, and by this first bound, for that weight to really count, but for it to sort of if that epsilon weight is really tend to 0, then you must have one of these xi's being big, that is one of these inner products being big. Okay, so this keeps it actually not so hard to prove. Okay, and now we're basically done. So if you just apply the key geometric lemma to our setting, we get this lemma in the setting of the colorings. So we get that there's this vertex, this color, this set, and this lambda given to us by the lemma, such that, and so in every color we only lose alpha, and in this particular color we gain lambda times alpha, and our set is not too small, right? So if lambda is -1, then we just lose a factor of epsilon as we wanted. So the first case is lambda is -1, say, in which case we have the thing we wanted, and x prime is at least epsilon times x. If lambda is large, on the other hand, then we lose a lot more here, but we gain back with this density boost. Right? And as I tried to explain before, then you just run this algorithm. Almost all the steps must be nice steps, and so you end up with a big book.
So I don't get why. So the lemma gives you lambda, you say, but I
Yeah.
thought like either lambda is either it's -1 as you said now, or it should be very large to.
Sorry. Yeah. So I'm cheating slightly. So I'm sort of not saying the right thing. So either it's bigger or smaller. So the threshold is this lambda 0. So we pick some large constant lambda 0.
Uh-huh.
It's either bigger than lambda 0 or smaller than lambda 0. So if it's
Uh-huh.
bigger than lambda 0, we're happy with a density boost.
Okay.
If it's smaller than lambda 0, then this whole thing is just a constant. So we don't lose epsilon, we lose epsilon times some other constant. We lose epsilon squared.
Okay. Okay.
Right. Yeah, so but lambda 0 is just a large constant, depending on R. Great. Okay, so all this part is then also just sort of is also not difficult at all. Okay. Okay, and now we're done. Okay, so that's basically the whole proof. Yeah. From there, you can sort of just fill in the details. Right. So our proof gives this value of delta and k needs to be this. So it even works up to r being like k to the little o1, but not beyond that. And so the most obvious open problem seems to be, can you do this for some delta that does not depend on r? Right. Which seems very much like it should be true. Yeah, our proof, I mean, very much requires some dependence on r in various different places. In particular, as was just pointed out, this 3r sort of immediately kills you. So if you wanted something that was independent of r, you need a better function f. So this is not a good enough function. Okay, if you were going to do it this way. Okay, so this seems like a nice open problem. It's probably perhaps the next sort of real challenge would be to do this, I think. And let me just finally tell you, just before finishing, this other geometric conjecture. So now, hopefully, I've persuaded you that geometric conjectures can be useful. So I guess we now don't have an application for this, or I mean, you could apply it to the two color problem. Maybe you get a better constant for two colors. So here's the conjecture that we wanted to prove. So there's no probability measure on the sphere, the D-dimensional sphere, that's both asymmetric and sub-Gaussian. So what does that mean? So asymmetric means that like more than half of your pairs of sort of pairs of points. Think of like n points on the sphere. Like 2/3 of them say have inner product that's minus constant over root d. Right, so you have this serious imbalance, like a surprising number of your pairs of points have negative inner product by like one standard deviation. Okay, so maybe think of this c as being one, and this half plus c as being 2/3. So, okay, I mean we can't prove it for sort of anything, so we'll make it whatever you like. And sub-Gaussian just means that you sort of look like a Gaussian in every direction. So instead, if you look like a Gaussian in every direction, then you should be symmetric. Right? Your inner product should be basically, positive, negative, probability of half. This seems like to me like an extremely, extremely natural conjecture that does not seem to have been considered by any of the communities of people we talk to. And right, seems very like, I mean, it would plug directly into this two color argument. And then perhaps there's some version of this that if you could prove it would then work for R colors as well. I mean, it's hard to say. But this seems to me perhaps like another really sort of exciting thing to try to work on if anyone has any kind of ideas. We tried a bunch of stuff and failed, but yeah, it really wouldn't amaze me if this is if there's some technique out there that just does this, or yeah, it's not clear. But this is sort of again getting to this the heart of this matter of in Ramsey theory, what you care about is negative correlation implies clustering. So this is negative correlation, and this failing is clustering. So that's the.
Does it make sense for some small value of d?
So I'm now not certain whether I think it doesn't make sense for small d, but you could say let d be large and n be say n be sufficiently large. Sorry, yeah, it makes sense. So yeah, sorry. So it doesn't make sense for small d. For a given, you want sort of this constant to be absolute and d tend to infinity.
That's true.
Yeah. Sorry. Yeah. Sorry. Yeah, I should have made that clear. Yeah. Yeah. Well, what we really care about is when this probability measure is a set of points of size 2 to the root d. But we can't prove it in for sort of any class of probability measures. So maybe that's a sort of a first step to maybe it's true for some particular sort of like continuous probability measures or something. Yeah. Anyway, I think this is yeah. I'm trying to advertise this conjecture as much as possible. I think it's a good direction. Anyway, sorry. Thanks for your